Okay, so in this video we're going to talk about exponential growth and decay. So there's a couple of definitions we want to talk about. Exponential growth. It can be modeled with the function y equals a to the bx, just like any other exponential function, where a is greater than 0 and b is less than, or no, excuse me, b is greater than or equal to 1, which is called the growth factor. Then there's exponential decay, where it can be modeled with the function, also the function a is times b to the x, where a is greater than 0, but now this time though, b is greater than 0 but less than 1. This is called the decay factor. Okay, so we have growth, we have decay. You hear about things growing exponentially, this is what we're talking about. So exponential growth, exponential decay. Here's our big equation, y equals a times b to the x. So a is going to represent our starting amount. It's going to be it's not going to be 0, our starting amount. So then we're going to have our exponent is going to be up here, b is going to be our base. Our base, if our base is between 0 and 1, we're going to be talking about decay. If our base is greater than 1, we're going to be talking about growth. And we're always going to have 100% positive or negative growth and decay. And I'll show you what I mean by that. Alright, so let's look at some examples of growth and decay. I hate exponential growth and decay. I find it very difficult. So hopefully you will not. So here's example 1. Suppose the population of a city is $50,000 and it's going to grow 3% each year. We're going to write an equation to model the population in X years. That's not so bad. Then we're going to predict the population after 25 years. So we've got our 50,000 up here. This is going to be our start. This 50,000 is going to be our A value. Then we're going to have our 3%. This marker works better. Maybe. So then we're going to have our 3%. And of course, you know 3% you have to rewrite as a decimal. And we've got our X years, we have our 25 years. So here's our equation. Here's going to be our A value. Remember how I said on the slide before this that we always work with 100%? So we're always going to have a 1. Our 1 plus something or our 1 minus something. Well, this is growth because we're growing 3%. So we're going to do 1 for our 100% plus something. Like I said, we go 100% plus or 100% minus for growth or decay. 1 plus here's our 3%, which we changed to a decimal because you can't work in percent. So we have our starting value of 50,000 times 1, that's our 100%, plus our growth factor. And then r to the x, because we're representing in X years. We don't know how many years. So here's our equation in X years. 50,000 times 1.03, because 1 plus 0.03 is just 1.03 to the x. Okay? Then we also wanted to we're going to predict the population after 25 years. So this time, we're going to replace our x with 25. So everything else stays the same. Our start value is still 50,000 times 1.03 to the 25. This is an equation we can actually solve. Everything is in there. We can just plug it into our calculator. So do 1.03 raised to the 25th power, multiply it times 50,000. You're going to get a big decimal. So if we round it up, we're going to find that in 25 years, the population of this city is about 104,689 people. So this is how exponential growth works. You can plug in numbers and find that population growth is this. This is a formula that scientists actually use to determine population growth. Okay, so what about decay? Where would we use decay? So, value of a new car. This is going to affect some of you before too long. The value of a new car decreases or decays exponentially. Suppose you buy a car for $22,000. Here's our dollars. Here's our A value. And the value of the car decreases at a rate of 20%. Here's our decay factor each year. Write an equation to model the value of the car in X years. Then, we're going to find the value of the car after 6 years. So here's our generic equation. Same one. We're going to do 22,000, that's our start value, times, here's 1, here's our 100%, just like before. This time we're doing minus, because it's a decay problem. Minus, and it was 20%, which we're going to change to 0.20, because again, we can't work with percent. And then to the x. So 1 minus 0.20 is the same as 80, or 0.80. So our equation for x years would be y equals 22,000 times 0.80 to the x. After 6 years, however, we're going to take out that x and put in a 6 because we're modeling 6 years. So our actual value of the car after 6 years, if we take 0.80 or 80 hundredths and raise it to the 6th power and then multiply it times 22,000, the actual value of the car after 6 years is $15,757.17. This is because of the decay rate, or the decreasing value of cars. They decrease at a rate, if it decreases at a rate of 20%. Some decrease at a higher rate, some decrease at a lower rate. That's what stinks about buying a car. Okay, so let's talk about something else. You're always asking, how do we apply math in real life? Well, here's a way. Here's how we're going to apply exponential growth. Compound interest. When a bank pays interest on both the principal and the interest in an account that an account has earned. This is called compound interest. We've talked about basic interest, where you learned this formula, I equals PRT. We learned that in 6th grade. This is compound interest. This is actually a little more to go, a little more involved. An interest period is the length of time over which interest is calculated. So let's say we're talking about compound interest. So compound interest, things are compounded either annually, which means once per year, and then we have our interest rate. And in this example, we're going to say 8% every year. It can be compounded biannually, which means twice per year, in which case you take your interest rate, divide it by 2, which means it comes out to be 4% every 6 months. Could be compounded quarterly, where you have 4 interest periods per year, which means you take that 8%, divide it by 4, which means you get an interest rate of 2%, and it happens every 3 months. Or it could be compounded monthly, which means 12 times per year, which means you take that interest rate of 8%, divide it by 12, and you're going to get 0.6666 repeating, and it happens every month. Fortunately, this is not something you have to worry about till you're a little older. However, we're going to use it to solve some problems involving exponential growth. So interest rates are something that will become an issue as you get older, but right now we're going to use it with our exponential growth. So let's solve a couple of problems using compound interest. I hope you just wrote that chart down. So find the balance in this account. If you start out with $500 in principal, and you're going to earn 4%, and it's going to be compounded quarterly. It's compounded quarterly, that means 4 times per year. That's what quarterly means. We have 4 quarters in our school year. How much money are you going to have after 6 years? So here's our same basic formula. Here's our starting rate. Our A value is 500. Remember, here's our 1 for 100%, plus it's going to be quarterly. So we're taking our interest rate, 4%, we're dividing it by 4, just like I did in my chart. Now, I'm going to take my 6 years, and I'm multiplying it by 4, again, because it was quarterly. Okay? So since I have to do 6 years, and it was compounded quarterly, so I have to divide this by 4 for quarterly, and multiply that by 4 for quarterly. So when I'm doing this, it comes into play twice. So now 0.04 divided by 4 just comes out to 0.01. So when I add 1 plus this, I get 1.01. So when I solve this, I get 1.01 to the 24th power times 500. So after 6 years, at 4% compounded quarterly, this account would have this much money, is how much it has earned. So really, I'm going to make this much money and add it back to that. All right. What about if I started out with $2,400 and I'm getting 7% and it's going to be compounded monthly for 10 years? So this time, I am earning more, it's being compounded more often, and it's going on for longer. Hopefully you've already said in your brain, well, this time I'm going to make more money. Well, let's see. 2,400 times 1 plus 0.07 divided by 12. Guess what? 0.07 divided by 12 gives you this nice long number taken to the 120. Remember, whatever you divide by here, you also have to multiply by up here. And this compound interest formula is actually a formula that we get into in math 2 a lot. So now 1.00583 repeating, you raise it up to the 1/20th power, multiply it times 2400, and this is the amount of money you're going to earn when you solve this problem. And again, you're adding it back to that. Alright, so this is a way that we actually put exponential growth to use in real life. And now we're going to do some more exponential growth and decay when you get to class tomorrow, so you'll understand it a little more in depth.